Alright, today we're going to start section 2.6 and we're going to be talking about rational functions. We're going to be looking at asymptotes and holes and other key things that we want to be able to identify in a rational function. So hopefully you have the rational functions or sketching rational functions sheet that I gave you today in class to help you with these notes. If you left it in class or lost it already, I did put it online as well, so you can grab it there. Okay, so we're going to go through that note sheet real quick, and we're going to use this rational function here to kind of help us go through that. So if we look at that sheet, the first thing here, it says factor. So when we have a rational function like we do here, it's useful in both the factored and the non-factored form, but we can get a lot more information in the factored form. So let's go ahead and factor this. So if I factor the numerator, I can take out a greatest common factor of x, and I end up with x times, it's going to be, let's see, 2x minus 3 and x minus 1. And in the denominator, we can take out a 3, and then we're left with x cubed plus 8, which is the sum of cubes, so that'll become x plus 2 times x squared minus 2x plus 4. And now, understanding the sum of cubes, I know that this quadratic trinomial is never going to factor into real coefficients. Okay, so now that we have the factored form, one thing that's nice about the factored form is it allows us to easily see what the domain of this rational function is going to be. So that's going to be, where does the denominator not exist? Well, I know, again, the quadratic trinomial is going to give me imaginary values, so I can ignore that. The only value that it's not going to exist is going to be x equals -2. So I know that the domain here is negative infinity to -2, -2 to infinity. Now, if we look back at our sheet, the next thing we want to look for is holes. So we want to look for holes next because holes take precedent over asymptotes and intercepts. So what we're looking for with holes is, does any of these factors cancel? If they do, then that's going to lead us to the x value of a hole, and we know that that's going to be a hole, and it's not going to be an asymptote or an x-intercept. In this case, nothing cancels, so I know no holes. But that would be the next thing we want to look for. Now we would look for x-intercepts and y-intercepts. So if we go back here, well, the x-intercepts are going to come from setting the numerator equal to 0 and solving for x. So I know that I'm going to have 0, 0, 3/2, 0, and 1, 0. Now this also led me to my y-intercept, which I get if I plug 0 in for x, and that's going to be the point 0, 0. Alright. Next, we want to look for vertical asymptotes. So vertical asymptotes are going to come from when the denominator equals 0, but is not a whole. So in this case, the only thing is going to be x equals -2. Vertical asymptotes and holes are going to be what makes the domain not exist. So in this case, this is my shorthand for vertical asymptote, VASI. I have x equals -2. Now we want to make sure to write the vertical asymptote as the equation of a vertical line. So I want to write x equals -2. I don't want to just write -2. And then I want to be very clear when I'm writing intercepts and write them as points. I don't want to write x equals 0 or x equals 3/2 as x-intercepts, because now I might get confused with vertical asymptotes. Now another thing real quick about vertical asymptotes is we want to understand that they do represent places where the function does not exist. So a function can never cross a vertical asymptote, whereas a horizontal or an oblique or slant asymptote, a function can cross those. With most of the functions we're dealing with, it's kind of rare, but it can cross those because those just guide the function. whereas a vertical asymptote, the function will not physically cross that point. Alright, so now we did the vertical asymptotes. Next thing we want to do is find the end behavior, which is going to directly relate to the horizontal or slant/oblique asymptotes. So what we're looking for here, we have our three scenarios that we can see at the bottom. So we want to compare the degree of the numerator to the degree of the denominator. And in this case, we can see that they're the same. The degree of the numerator is 3, the degree of the denominator is 3. So I can look at my scenario if n equals m, the graph of f has the line y equals a sub n over b sub m as our horizontal asymptote. Well, a sub n and b sub m are the leading coefficients of the polynomial in the numerator and the polynomial in the denominator. So in this case, that's 2 and 3. So I have a horizontal asymptote of y equals 2/3. Again, I want to be very careful to make sure I write y equals because it is the equation of a line. Now, I can never have a horizontal and a slant or oblique asymptote. So slant asymptote is none. And we're not really going to look at a slant asymptote on this problem, obviously. But to find a slant asymptote, we would actually do the division, divide the numerator by the denominator, and that result, the quotient, ignoring the remainder, is the slant asymptote. It should be the equation of a line. If we have some other sort of oblique asymptote, so a slant asymptote is a very specific one, then it could be the equation of a quadratic or a cubic. It's whatever the quotient is, though. That's the oblique asymptote. Okay, so then on this sheet here, it talks about end behavior, and end behavior again is the slant, oblique, or horizontal asymptotes. So in this case, since the horizontal asymptote is y equals 2/3, I know as x goes to infinity and as x goes to negative infinity, the function is going to approach 2/3. So that is my end behavior. And then the other thing it talks about here, we're not actually going to sketch this curve, but determining sign in intervals between zeros and asymptotes. So if we were to sketch this by hand, what we would want to do is figure out as much information as we can. So we would look between the x-intercepts, the y-intercept, those are the points that we already know, and the vertical asymptote, and pick some other x values to determine are we above or below the horizontal asymptote at those points. Okay, so now I want you to try this on your own. So here you have the function f of x equals 2 minus 3 over x squared. I want you to find the domain, the horizontal asymptote, the vertical asymptote, the whole, the x-intercept, and the y-intercept, and then actually plot and graph the function to the best of your ability. It does not have to be exact, but all of this information, the asymptotes and the intercepts, those should be exact and in the general shape of the curve. So pause the video and unpause it when you are ready to check your answer. Alright, so let's check your information. I have the domain is negative infinity to 0, 0 to infinity. The horizontal asymptote is y equals 2. The vertical asymptote is x equals 0. There is no hole. There are two x-intercepts. One is at root 6 over 2, comma 0, and the other is at negative root 6 over 2, comma 0. And the y-intercept, there is no y-intercept because then we have a vertical asymptote of x equals 0. So then my graph, I drew my vertical asymptote as this dashed line at 0. My horizontal asymptote is this dashed line at 2. I put in my two x-intercepts. Root 6 over 2 I know is somewhere between 1 and 1.5. And then I draw the general sketch of the curve. Remember, I know it's going to approach the horizontal and the vertical asymptotes. I knew that it was below the horizontal asymptote because I knew it had to go through those two x-intercepts. Up here you can see my work to find the x-intercepts. I rationalized the denominator. That's how I got root 6 over 2. Here also notice one other thing I did at the beginning was I made this a single rational function by getting a common denominator, and so then it was a little bit easier for me to see some of the details about the actual function. Okay, same thing here. So I want you to pause the video in a minute, and I want you to find the domain, the horizontal asymptote, the vertical asymptote, the whole, the x-intercept, and the y-intercept, and then do a sketch of the function for h of x here. So pause the video and unpause it when you're ready to. Okay, so you might have gotten a little stuck on this one if you didn't remember doing holes before, but this one has a hole. So when I first factor this, I get x plus 4 times x minus 4 over x plus 4 times x minus 3. The x plus 4's cancel. As soon as I see that happen, I go right down to the line that says whole, and I write -4 in the x spot. Because I know that whatever canceled, so in this case x plus 4, whatever makes that 0, which in this case is a -4 for x. So, you know, if I do x plus 4 equals 0, and x equals -4. So that's how I got -4. That is the x value of the whole. How do I find the y value of the whole? Well, I use what I call the reduced function. So whatever is left over, x minus 4 over x minus 3, this is what I'm going to call the reduced function. Everything comes from the reduced function on here. So the horizontal asymptote, the vertical asymptote, the y value of the whole, the x-intercept and the y-intercept all come from the reduced function. The only thing that came from the original function is the domain and the x value of the whole. So to get the y value of the whole, I plugged in the x value to the reduced function, and that's how I got 8/7. So I know I have a whole at -4 8/7. I have an x-intercept at 4, 0, a y-intercept at 0, 4/3. Again, those both come from the reduced function. The domain is from the original function, -infinity to -4, -4 to 3, 3 to infinity. Horizontal asymptote is y equals 1. Vertical asymptote is x equals 3. So now when I graph this, plot the asymptotes, again, dashed lines, plot the intercepts, plot the whole, make it very obvious that it's a whole, and then draw the general shape of the function. Again, in this case, because of where the intercepts were and the whole, and the fact that I know asymptotes have to guide the function, I know what the shape of this graph is going to look like. If I wanted to be more precise, I could pick a couple other x values, but this is all I'm really looking for, is to get the general shape correct. Okay, last one. Again, here's a function, x squared minus 4 over x plus 2, and I want you to find the domain, horizontal, vertical, asymptotes, whole, x-intercept, y-intercept, and draw a general sketch of the function. So pause the video, unpause it when you're ready to check your answer. Okay, so again, there was a little trick to this one. In this case, again, we have a whole. So I factor in x plus 2 times x minus 2 over x plus 2. The x plus 2's cancel, so I know that the x value of the whole is -2. To find the y value of the whole, I plugged that into the reduced function. Notice that the reduced function is not a rational function anymore. It doesn't affect the y value of the whole. The y value of the whole is -4, so I know I have a whole at -2, -4. But it does affect some other things. So my domain, again, comes from the original function. It's -infinity to -2 to infinity. But because my reduced function is not a rational function anymore, it's just a linear function, I don't have any asymptotes. So there is no denominator still to set equal to 0, so there's no vertical asymptote, and there's no degree of the denominator to compare the horizontal or the numerator to. So I have no horizontal asymptote. I have an x-intercept at 2, 0, a y-intercept at 0, -2. So this is actually just, our graph here is the equation of the line y equals x minus 2, except for it has a whole at -2, -4. So it has a slope of +1, y-intercept of -2, x-intercept of 2, and then again make your whole really obvious. Okay, so just to kind of conclude, and you already have a lot of this on your sheet that I gave you, but the domain, we set the denominator of the original function equal to 0 and solve for x. Vertical asymptote, set the denominator of the reduced function equal to 0 and solve for x. Obviously, if the function doesn't reduce, then you're using the original function. For a whole, if something in the original function cancels, that leads to the x value of the whole. Plug that into the reduced function to obtain the y value of the whole. Horizontal asymptotes, use the reduced function to test the 3 scenarios with regards to the degree of the numerator versus the degree of the denominator. X-intercept, set the numerator of the reduced function equal to 0 and solve for x. Y-intercept, plug in 0 for x into the reduced function.